Welcome to another episode of Learning. I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of the problems that appeared in the CSIR National Eligibility Test held on February 28, 2025. In this video, we discuss the solution of a problem from the section Linear Algebra, and the problem is related to the dimensions of certain subspaces. This question is placed in part C, which is a multiple select question. There can be more than one answer, and the question carries 4.75 marks. The question ID is 704152. This question is suitable for all these examinations. Right. The given question is, for a variable x, consider Q vector space, capital V, is equal to the set of all ax cube plus bx square plus cx plus d, where a, b, c, d belongs to Q. Further, let A is equal to the set of all f from V to Q, where f is a Q linear transformation, and capital B is a set of all f belongs to A such that f of 1 is equal to 0. Which of the following statements are true? We are given four options. Option 1. If f belongs to B, then the dimension of ker f is equal to 3. Option 2. Dimension of B is equal to 3. Option 3. Dimension of A is equal to 4. Option 4. If f belongs to A, then the image of f is a one-dimensional Q vector space. Let's now discuss the solution of the problem in detail. We are given V is equal to the set of all ax cube plus bx square plus cx plus d, where a, b, c, d belongs to Q, a vector space over Q. What is this vector space? It is a vector space of all polynomials of degree at most 3 over Q. That means the coefficients are coming from Q. That is Q3 bracket x, that is, and over Q. This is the vector space of all polynomials of degree at most 3 in one indeterminate x with the coefficients coming from Q. That's a vector space over Q. The standard basis of V is 1 x, x square, x cube. And the dimension of V over Q is 4. Given A is a set of all f such that V to Q, where f is a Q linear transformation. That is, A consisting of the set of all Q linear transformations from V to Q. That is, this is the vector space of L, V, comma, Q. That means V to Q, LUV. You remember the vector space LUV. The set of all linear transformations from U to V, that is forms a vector space, and that is LUV. And here U is V In the place of V, we have Q. And you know the dimension of LUV will be the dimension of U multiplied by the dimension of V. And mind you, U and V are vector spaces over the same field F. And both are finite dimensional. Then the formula is the dimension of LUV is equal to the dimension of U multiplied by the dimension of V. Right. Option 3 is dimension of A is equal to 4. Now, dimension of A is dimension of L of V comma Q, LUV, that is equal to dimension of V over Q. V is a vector space over Q, Q is a vector space over Q, over the same vector space. The dimension of V over Q multiplied by the dimension of Q over Q. The dimension of U over Q is 4. The dimension of Q over Q is 1. That is 4. Yes, dimension of A is 4 is true. Therefore, the option 3 is true. We move to the next option, and before that, we are given B is equal to the set of all those F, that is Q linear transformations that belong to A, such that F of 1 is 0. Clearly, B is a subspace of A. Yes, B is a subspace of A. Now, option 2, dimension of B is 3. We have B is a subspace of A, and the dimension of A is 4. And you know, look at B, each linear transformation F in B satisfies the condition F of 1 is equal to 0. That means there is a restriction. There is a restriction on the elements of F belongs to A. That is F of 1 is equal to 0. So therefore, the dimension of B is equal to the dimension of A minus the number of linearly independent restrictions. How many linearly independent restrictions are there? One linearly independent, that is F of 1 is equal to, each F belongs to A has the restriction F of 1 is equal to 0. So the number of linearly independent restrictions is 1. 4 minus 1 is equal to 3. So thus dimension of B is 3 is true. Option 2 is true. Right. We move to the next slide for the discussion of the remaining options. Option 4. If F belongs to A, then the image of F is a one-dimensional Q vector space. F belongs to A, an arbitrary element of A. If F belongs to A means F is any element of A. For that, the image of F is a one-dimensional Q vector space. Now, when this is true for every linear transformation of A, why not we take the zero linear transformation? That means zero linear transformation is that transformation which takes every polynomial to 0 of Q. Let F be the zero linear transformation in A. That is, F takes every polynomial P of x to 0 in Q. That is, F of Px is equal to 0 for all Px belongs to V. Now, the image of F is the set of all images of the polynomials under the linear transformation F. The set of all F of Px belongs to V. And F is a zero linear transformation. F of Px is 0 for all Px belongs to V. Therefore, it is a singleton 0. And image of F is a subspace. Image of F is a subspace of Q. So its dimension over Q is 0. Its dimension over Q is 0. But in option 4, it says it is a one-dimensional Q vector space. Therefore, option 4 is not true. We move on to option 1. If f belongs to B, then the dimension of kernel of f is 3. Right. Now we consider, let f be the zero linear transformation in A. Then f will send every polynomial to zero element of Q for all Px belongs to V. Naturally, 1 is also a polynomial of degree 0. Therefore, f of 1 also will go to 0. So, f of 1 is equal to 0. Therefore, f belongs to B. Therefore, our zero linear transformation, what we have considered, is also an element of B. For that is the dimension of the kernel of f is 3. Now, kernel of f is what? Kernel of f is the set of all those polynomials which are sent to the zero element of Q. Who are they? Every polynomial. Therefore, it is whole of V. The kernel of f is V and its dimension V over Q. The dimension of V is 4. So, its dimension over Q is 4. But it is given to be dimension of kernel of f. Dimension of kernel of f is 3. Therefore, option 1 is not true. Thus, the combining all the options, we get the answer. The answer to this question is options 2 and 3. That is the detailed discussion of the solution of the given problem from the section linear algebra, which is based on the dimensions of certain subspaces given in the question. And this is not a difficult question. I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. I am sure that we are going to meet you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.